Welcome back to Mr. Halberstadt's videos. Today we're going to be talking about the basics of waves. Aren't you excited to be hearing my voice again? So let's get right into it. The first thing we're going to talk about is something that you all have seen previously. Now, if you take a ball, this is on the left a ball, and you throw it, you give it some velocity, it will travel from one location to another. It will end up with some velocity at that second location, and it will also end up with some mass, so velocity and mass. Because we have a velocity and a mass, we end up with energy. So we put energy into the ball, and the ball moves. So we end up with energy at our second location, and we end up with mass at our second location. A wave is going to do something similar. It's going to take energy, you're going to put energy into a system, and so it creates this disturbance. So let's imagine that this line down here is just a slinky, right? We create this disturbance in it, and we move the disturbance down the slinky. So this little disturbance is going to move with some velocity v, and when it gets to the other end, it will have energy. However, if you notice, this slinky didn't move. So we had a slinky going the entire length, and we started with some velocity, we ended up with some velocity, we ended up moving energy, but we did not move mass. So that's essentially what a wave is going to be. It's a disturbance that travels through a medium. When we say a medium, we just mean some sort of substance that the wave travels through. In this example, the medium is the slinky. And it's a disturbance that travels through a medium that moves energy without moving mass. See there, we have energy, but we did not move mass. So let's talk about a few of the different types of waves. Now, there are two main types of waves that we're going to be talking about. We're going to be talking about longitudinal waves, and we're going to be talking about transverse waves. So first, for a longitudinal wave. Now, a longitudinal wave is a type of wave that deals with compressions and rarefactions. So what you would look for when you're seeing a longitudinal wave, let's draw some lines to show kind of what compression and rarefaction looks like. This right here at the top is an example of a longitudinal wave. We have this area right here where our lines are really, really close together. That's an area of compression. And we have the areas where the lines are spreading apart. That's called a rarefaction. Essentially, when we look at a wave, if we want to figure out if it's longitudinal, we want to look at the direction that the wave is traveling and the direction of the disturbance in the medium. So a longitudinal wave, the wave here overall is traveling to the right, so this arrow is the direction of the wave travel, and the compression and rarefactions are happening left to right. So we have a compression here, and then we have a rarefaction here. I know it's kind of hard to see because I have all those things drawn on top of each other, but if you look at this spot here, it's compressing in from the left and the right. And then here it's spreading out from the left and the right. So the disturbance in the medium is left and right, and the motion of the wave overall is from left to right. So that gives us a longitudinal wave. Now, by comparison, a transverse wave is not going to look quite the same. In a transverse wave, we still have the motion of our wave from left to right. Our disturbance is moving to the right. It also could be moving to the left. In this example, it's not really clear for either of them. But the disturbance in the medium is up and down. So it either goes up or down. So because the disturbance is in the opposite direction as the motion, so the wave is moving to the right, but the disturbance in the medium is up and down, we get a transverse wave. Now, if you've heard of other words that have this trans prefix, trans usually means opposite or motion or different or something like that. So transverse means opposite direction. We have motion in one direction and displacement in the other. So we have a few different types of waves here. We have light waves, we have sound waves, we have ripples and other sorts of physical waves. And let's figure out which one belongs where. So light waves are actually going to be a type of transverse wave. Now, we can get into a few more details later on, and it's really pretty high level what exactly the medium is and all that stuff, and there really isn't a medium for light waves and stuff, but it is a transverse wave. The disturbance is happening in one direction, up and down, and the motion of the wave is happening in a different direction. Sound, however, is a longitudinal type of wave. So when we're dealing with sound, that's what we are, when I speak, there is a compression that my voice creates of the air in front of me, and that compression propagates forward. So because we're dealing with compressions and rarefactions, then that is going to be a longitudinal wave. Now, if we're looking at things like ripples, that move through either water or move through a, let's say you punch a wall and you see those ripples that travel through that way. Those sort of waves can be either longitudinal or transverse. It just kind of depends. Ripples through water are going to be transverse, whereas ripples in a wall, if you like tap on a wall or hit a wall, those vibrations are going to move out in a longitudinal fashion. So those can be either or. Typically ripples are going to be more on the transverse side, but in this example, but there are examples of it that are going to be longitudinal. So let's start with some basics of waves. So if we had a ball and we threw it, gave it some velocity, the same example as before, and it moved a certain distance, we could figure out what the distance is, and we can figure out a relationship that deals with distance, velocity, and time. So if we have the distance, that's going to be equal to our velocity times our time. This just goes back to our kinematics that we have used before. So if we wanted to figure out the amount of time it took for the ball to travel, we could rearrange this equation, take our distance, divide it by our velocity, and that would give us the amount of time it takes to travel from this point to the next. Now, with waves, we can use the exact same equation. So if we have a disturbance in our wave that starts over here on the left and travels a distance d, and we know that the wave disturbance is moving with a certain velocity, we can use the exact same equation, but just use the values that we had for the wave. So basically what this is talking about is that a wave, even though we're not moving a physical ball, we can use the same equation that we use from kinematics. Distance equals velocity times time. Now, how do waves distinguish themselves from one another? There's a few different variables that we can use to talk about what a different wave is. So the first one that I'm going to talk about should be familiar to you from simple harmonic oscillators, is going to be this A right here. This is going to be the amplitude of the wave. Now you can have a positive amplitude like we have here on the left, or a negative amplitude like we have here in the middle, but this is basically going to be the maximum displacement from our equilibrium line. So it's exactly the same thing that we had from before when we were dealing with simple harmonic oscillators. Now your amplitude may be a distance if we're dealing with a transverse wave, or if we're dealing with a longitudinal wave where we have this compression rarefaction, your amplitude is actually going to be an amount of pressure. So here we have positive pressure because things are really tight together. Here we have negative pressure because things are really spread out. Now there's a few other things that we can talk about. Here we have what's called the crest of the wave. and here we have the trough. This is basically the top part where we measure the amplitude and the bottom part where we measure the amplitude. Now, if we are taking the distance between one crest and another, this also has a fancy name. This is called the wavelength. And the wavelength of a wave, we use the symbol lambda, or an upside down Y, kind of a stick man that's kind of leaning backwards without a head. I don't know, there's a few different ways you can look at it. So this wavelength is the distance that a wave takes from peak to peak, or from trough to trough. Now, unlike in the last chapter when we were talking about this peak to peak, we call this peak to peak thing the period, and we'll talk a little bit about time. But here, the axis, if we check what the axis is, it's in meters. So this right here is measuring an amount of distance. So our wavelength is going to actually be measured in meters. Our amplitude, like I said before, can have a few different variables. So let's talk about these different two equations that we have. So we have, first, we've talked about velocity, and that tells us how quickly a wave is moving. But in the last slide, we also introduced this idea of a wavelength. So how could we talk about velocity and wavelength in one equation, in one idea? Well, if we look at our units here, we have meters per second, and then we have meters. So if we take velocity and divide it by our wavelength, this is going to give us something that is in units of 1/seconds. Who remembers what that is? That's right, the unit for 1/seconds is hertz. And if you remember, when we were measuring the amount of hertz that something had, or the number of cycles in a second, that was called the frequency. So, we're going to use that same notation here. And so we already found that our frequency is going to be equal to our velocity over our wavelength. So this equation is usually rearranged to be velocity equals frequency times wavelength. So this is going to be the final equation that we use in this chapter. Now, typically, this velocity term is just a factor of the medium. So it doesn't make a difference how softly I talk or how loud I scream. The velocity of that sound is going to be the same. Just like in simple harmonic motion, the amount of volume or the amount of energy that is contained within a wave is dependent on its amplitude, not on its velocity. So this velocity as a factor of the medium is going to be constant in the same medium. So if we keep the medium the same, and let's pretend that we increase the frequency, we're going to see an equal decrease in the wavelength. So that means that frequency and wavelength are inversely proportional. When one goes up, the other one has to go down. When one goes down, the other one has to go up, if we're keeping the medium the same. So that's all that we have for the basics of waves. Next, we're going to talk a little bit about what happens when two waves collide or waves hit other things and how they react when they run into stuff.